Okay, so we're going to run through a Thevenin question for obviously purpose of practice with the exam. So we'll draw up a circuit. We're going to take a source and put in a capacitor, and we'll go with resistor and inductor. We'll go positive J 6 ohms, 5 ohms, and that'll be negative then J. We'll go 4 ohms for the capacitor. A very badly drawn capacitor with the say longer lines, but hope you get the point. Voltage, let's go 30 volts. Keep an angle 0 degrees, do fine. And then from here we're going to connect out to 2 points. We call it A, very badly drawn A, and B, and we're going to have a load on here of 6 ohms and inductor 12. J12 ohms. You can put positive in there if you want. I didn't for the other bit anyway. And we're going to try and find, so determine, let's see, current in the load. But not very good to write Z for L instead, was it? Determine the current in the load and the voltage. Pardon me, across the load as well. So we're going to try and find basically the current in this section in here, and then the voltage across said item effectively, which is together, we'll call it ZL, which would be 6 plus J12 as the load. Right, so stage one then, I suppose, is disconnect the load. So to do that, we can redraw, I suppose, very quickly, but we have a supply to capacitor, resistor, inductor, 30 volt, 0 ohms minus J 4 ohms. That was 5 ohms, and that was positive 6, or J6 rather. For that section, and then we go to open terminal basically, sections here, which is going to be A and B here, which is going to produce our voltage Thevenin at this point. So at this stage, we've disconnected the load, and we want to find the voltage across this 5 and 6 ohm load, 5 ohm resistor and the 6 ohm inductor, that is. So we're basically trying to find the voltage across that. You could redraw slightly again to B, if you sort of think of it in terms of the voltage divider, more a case of split it into 2 parts here as best as possible. But we're effectively getting that section there. So what you're trying to get out, the voltage of that. And you could use the voltage divider formula. So for instance, you could do R2 over R1 plus R2 multiplied by Vn would be your V out. But it would means we need to add and multiply and so on complex numbers, which isn't just as easy. There is a slightly easier method. In my estimation anyway. And to do that, we find the current in this loop here. Right, we're now in part of a series circuit for this section of it. So this section here, if you will, I'm sort of highlighting very badly over. But that there is a single series current flying through there. Nothing goes via A or via B because they don't go anywhere else, they're not connected. Therefore, you're not going to actually witness obviously anything occur. I'll just delete that back out. probably a better pen to write with. Anyway, so to calculate the current in the loop, so I call I loop, and that is effectively going to be the Ohm's law of V over R. Okay, now we don't actually have R in this instance. What we do have is V over our impedance Z. So the voltage in that circuit is quite simply the supply side of it, which is going to be your 30 volts angle 0 degrees, and our impedance of this, so your Z, is made by the series connected part of 1, 2 and 3 parts here. So that becomes our, we put the ohms bit in first, so 5 ohms plus 6J minus J4, I should really say it that way, right? Which very easily gives us a 30 volt angle 0 degrees over our 5, and that becomes J2 for that particular bit. Now, we need to obviously do division here. And the easiest way to do that is convert to polar. No. So convert to polar, so we leave that as 30 angle 0, and then we get the calculator here, and we go shift pole 5, 2, close brackets, and we end up with 5.39 angle 21.80. That would be to 2 decimal places. And then if we actually calculate that as an answer, just down below, so we do our real numbers, so 30 divided by 5.39 gives me 5.57, and then angle, so 0 minus 21.28, so it becomes negative 21.80. And that is what we're calculating here, current, so I loop. So that is going to be in amps then. That works out as. You could put it into polar if you so wish to, but we're not really required. So we've now got the current in this loop that we're talking about up here in the top left of the diagram. And now we want to find out the voltage across that. So it's very simple, back to Ohm's law. So V of the parallel section is equal to the current that's traveling through multiplied by the impedance of the parallel branch we're talking about. And what we mean by that is that's going to be our 5.57 angle negative 21.80, that's in amps, multiplied by the parallel branch. So that is 5 plus J6. 5 plus J6. So that there is very simply, let's do a different colour, let's go red. That is very simply this bit here. So basically what is the impedance of that section multiplied by the current flowing through it will give you the voltage across that element of it. So going back to here, obviously not very nice method in terms of polar and rectangular, so we need to convert the one on the right hand side. So we go shift rect, and that's 5, 6, close brackets, and that leaves us with 5,6 leaves us with 5.57 angle negative 21.80, and that's going to be multiplied by, just put those in brackets for now, and I'm being silly because I wanted to convert to polar. That would be even better. Trying to convert to rectangular apparently. So this in here we convert to polar. We already were in rectangular. 7.81, and we are angle 50.19. I was wondering why the number came up looking a bit odd. So we've converted from the 5 plus J6, which is in rectangular, to the polar version of it, so we can do a multiplication a bit easier. And then we now multiply the real number, so 5.57 multiplied by 7.81 gives us a 43.50, the 2 decimal places. And then the angle is, see, negative 21.8, and we're multiplying, so that means you add on 50.19, leaves us with an angle of 28.39 degrees, and that is measured in volts. So that is the voltage in the parallel section. So that there is effectively then your Thevenin voltage. Okay, so you've calculated the voltage across this red box section, which is therefore the exact same parallel bit as the voltage between A and B, which we've said is your Thevenin voltage. So VTH is equal to 43.50 angle 28.39 degrees measured in volts. Okay, so the next stage is, I suppose, we want to find out RTH, or Thevenin voltage, or ZTH, because it's going to be an impedance, I suppose we should really say. Right, because it has complex parts to it. So that therefore ZTH is going to be our diagram. So we remove our source, which is a 30. The negative 4J becomes on the left hand side. So negative J 4 ohms, which is your capacitor, is in parallel with a resistor of 5 ohms and an inductor of J 6 ohms, which is supposed to offers out to A and B here if you wish. And from that we need to determine, looking in, as you sometimes talk about, looking in, what is the impedance. So basically you're saying that the 5 and the J6 are in series with each other, but those are in parallel with the secondary branch, which is negative J4. So we can use the standard method here for ZTH. It's going to be product over sum. So we say that the product of those two, so we take 5 plus J6, and we're multiplying by negative J4, and that is then over the sum of the two, so it's 5 plus J6 plus, I should write in here, negative J4. So we'll do the bottom line first, which is pretty easy. So the plus J6 and the minus J4 become our 5 plus J2, similar to what we've done before. And then the top section here, we need to multiply our terms. So we have 5 multiplied by negative J4, which is then J, or negative J I should say, 20. And then the other section here is plus J6 and negative J4 multiplied by each other. So observing your polarity, it becomes negative J squared, and then 6 fours are 24. Now, if you remember, J squared is equal to negative 1. So applying that principle into here, we then say that it's negative J20. It's minus 1, so it becomes positive 24, and still over our 5 plus J2. Now, we've got a division going on here, so to do division, what we really want is our values to be effectively in polar, so let's convert both to polar. So that is just write it in a better format. So 24 minus J20 and 5 plus J2 becomes, let's see, shift pole 24 comma negative 20 becomes 31.24 angle negative 39.81 to 2 decimal places. And the bottom line, we go shift pole 5 plus J2, close brackets around it, becomes 5.39 angle 21.80. Feel as if we've done that before. So I actually do the calculation this time. 31.24 divided by 5.39 gives the 5.795, so that's 80, the 2 decimal places. And the angle is negative 39.81, and we're minusing 21.80 from it. Gives us negative 61.61. and that is going to be ohms, because we're measuring the Thevenin resistance. So that is our ZTH is 5.80 angle negative 61.61 ohms. Okay, so we now have a Thevenin equivalent circuit we can draw. So we have a power source and series connected resistance. Our points A and points B. So our Thevenin voltage was 43.5. Angle 28.39. And that's in volts. And our ZTH we just discovered there is 5.80 angle negative 61.61, and that is ohms. And we now connect in our load, which is a resistor and inductor at 6 and 12. So 6 ohms, and don't have to do it in dash lines. I'm just could have just changed colours, but sure, here we are. So that's now the load. So once we have that section done, what we're now able to do is basically find out with that the current in the load. So the current in the load is going to be equal to Ohm's law V over Z in this case. And just to clarify, it's going to be VTH over ZTH plus ZL. So that's the impedance of the Thevenin circuit plus the impedance of the load. So basically now what we have is one series circuit again this time. So the impedances can just be added together. So let's put in some values. So IL is equal to, so that is 43.50 angle 28.39. That's in volts. And then our ZTH is our 5.80 angle negative 61.61. Put that in brackets. And we're adding on our 6 plus J. It's pretty written, but 12. Okay, now, one of these in polar, nobody this one. It's easier if we convert to rectangular to add. So let's do that. Move over to the left-hand side a bit. 43.5 and angle 28.39 over, and then let's convert that. So shift rect 5.80 comma negative 61.61 comes out as 2.76 to 2 decimal places minus J 5.10, and then we are adding to that the 6 plus J 12. So with the real section of it, we do 2.76, and we're adding on the 6 to it just, which gives us a 43.50 angle 28.39, and that is 8.76. And then that is, let's see, negative 5.10, and we're adding on 12, which is positive J 6.9. That, just go over to the right here, is, we want to convert the bottom bit to polar. Oh. So this section here, we're going to convert to polar, which gives us 43.50, because we're about to do a division, 28.39 over, and then shift pole, 8.76 plus nothing, rather, put a comma in, 6.9, and that is 11.15 angle 38.23 to 2 decimal places. So let's do the division. 43.50 divided by 11.15, which is 3.90 angle, so 28.39, and we're dividing, so it's a minus 38.23. which gives us negative 9.84. And we are calculating IL, should really write in here. Therefore that there is in amps. Okay, so the original part of the question here, current in the load is 3.90, angle negative 9.84 degrees amps. And that gives you that part of the answer. And then the other bit we're asked for is the voltage in the load section, which is going to be equal to the current in the load multiplied by the impedance in the load, basically Ohm's law again. So we already know IL, we literally just calculated it. So 3.90 angle negative 9.84 degrees in amps. And we are multiplying by ZL, which is, there it is there, 6 plus J12. So 6 plus J12. And we want to convert this one to polar to do the multiplication. So shift pole 6, 12 is 13.42. Angle 63.43 degrees. And obviously that just gets written in again. 9.84 multiplied together. That gives us 3.90 multiplied by 13.42. 42, which is 52.34. And then the angle is negative 9.84. And we're multiplying, so we add on 63.43. And that gives us 53.59 degrees, and that is what we're calculating here, VL, so that's volts. And that there would be your secondary answer then. So voltage on the load would be 52.34, angle 53.54 volts. And that is a Thevenin's based question on complex numbers.